Section 29 of The Science History of the Universe, Volume 2. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Avai in January 2016. The Science History of the Universe, Volume 2, edited by Francis Rolt Wheeler. Geology. Chapter 14, Crystallography, Part 2. Most of the crystals of minerals would give a very poor impression of nature's workmanship to one who expected always to see them exactly like carefully made models or like the regular geometrical figures drawn of them. The cubes of galena are often flattened or drawn out. But it is not really to be supposed that the forms are badly made, like a bad model. On the contrary, the size of the like faces on a crystal may vary, and so the shape of the solid as a whole, but the angles between them remain the same. Moreover, what is really essential is not the size or shape of each face, but the way in which the little molecules of which the whole is built up are arranged. For example, in a cube, the essential point is the fact that the structure is the same in the direction of the three cubic faces. It follows from this that in the cube not only are the angles between two adjacent faces always 90 degrees, but the 6 cubic faces are all similar, and therefore, if there is the easy fracture, called cleavage, parallel to one cubic face, there will be also the same cleavage parallel to the others. But the actual size of the faces is a matter of no importance. In fact, in one species the cubes are sometimes lengthened so as to be like fine hairs. Similar remarks can be made in regard to any distorted form. The symmetry in the molecular structure, and hence the angles between the faces, remain unchanged, although the symmetry of the external geometrical form is not that of the ideal crystal. A cube may in nature look like a square prism, for the angles between the faces are all right angles in both cases, but the molecular structure of the two is not to be confounded. In the square prism there is the same arrangement in the transverse directions, but a different one up and down. Hence the square top of the crystal is not like the 4 similar oblong vertical faces, and there is cleavage parallel to one set and not to the other. From this variation it is evident that the practical study of natural crystals is much more difficult than the study of the models which gave the ideal forms. This is especially true because most crystals are so implanted on the rock or embedded in it that only part of the form has been developed. Thus, quartz crystals are often attached at one extremity, while only the other end has had a chance to grow freely. Or the crystals may be implanted upon a surface of rock so that only a series of minute faces and angles are visible. In such cases, the study of the form is really a difficult matter requiring much skill and experience. Besides the crystals that have been just spoken of, which, while they look at first irregular, are really perfect in the matter of the position of the faces and of the angles between them, there are others which are really deformed. Some peculiar condition attending the growth of the crystal, or perhaps some force which has acted upon it since it was formed, has resulted in bending or twisting it out of its normal shape, so that it may differ widely in angle from the regular form. Thus the faces may be curved as with the barrel-shaped crystals of pyromorphite, or like the peculiar convex faces common on crystals of the diamond, or the whole crystal may be bent, as is seen sometimes in crystals of quartz, stibnite, or of some kinds of chlorite. Aside from this curving and twisting, a crystal may have had its shape more or less changed by some force exerted in the rock since it was made. It may even have been broken and again cemented together, so that many irregularities may result. The salt crystals sometimes show distinctly one face only with the depression in the center, so that they are called hopper-shaped crystals. The cavernous crystals of pyromorphite and vanadinite give other examples. Crystals, often for the same reason, enclose foreign substances, sometimes in the form of liquids, as the quartz crystals that contain water, occasionally with a movable bubble of air. Or the liquid may be carbon dioxide, then often with a bubble of the same substance in the form of gas. In such cases the crystal must have been formed under great pressure, sufficient to keep the gas in the liquid form. Fragments of such crystals heated in the gas flame fly to pieces with great violence, because of the expansion of the gas formed from the liquid by heat. A peculiar class of false forms in which the crystalline shape does not belong to the chemical substance must be briefly described here. These are called pseudomorphs. Pseudomorph means false form, and the name is applied to a specimen having the form characteristic of one species and the chemical composition of another. This seemingly difficult contradiction is easily explained. Most chemical compounds are liable to undergo a change or alteration when subjected to certain conditions, as moisture, the action of alkaline waters, or acid vapors. Now, in these cases, if the original mineral was in crystals, the external form is usually preserved, often perfectly, while the chemical nature and the molecular structure have changed. The cases where the original substance has entirely disappeared and some other has come in to take its place are also called pseudomorphs. Thus, occasionally, quartz is found in the form of calcite, or of fluorite, or of barite, that is, pseudomorph after one of these. Also tinstone in the form of orthoclase feldspar, native copper in the form of aragonite. Even fossil wood may be said to be a pseudomorph of quartz or opal after the original wood, the structure of which it sometimes preserves with wonderful perfection. Some crystals occur isolated and alone, and then the form is usually developed on all sides, and with something of the regularity which the ideal model shows. Thus are found perfect garnets in mica schist or granite, and gypsum crystals in clay. But it is still more common to find crystals grouped together either irregularly, as in the majority of cases, or perhaps in parallel position, or again in the peculiar way called twinning. It is evident that, since the crystals on a single specimen of a species may be grouped in a great variety of ways, it is not always easy to decide whether a given case is a twin or not. This often becomes a matter requiring careful study, exact measurement of angles, and calculation, perhaps also of optical study. For example, it is common to find quartz crystals crossing each other at a great variety of angles, but true quartz twins are rare. The two parts of a true twin are usually symmetrical with reference to the twinning plane, and there is always the reversal of one half. One very common case of the grouping of crystals, which is apt to be confounded with twinning, is where the crystals or parts of crystals are parallel to each other, so that the axes of all have the same directions and are not inclined as in most twins. This is illustrated by a pile of cubes with faces parallel and having re-entrant angles between them. The crystals of many species are at times arranged in this way, but in every case it will be found that if the complex group is held so as to reflect the light from a window, the faces in adjoining crystals, which reflect at the same time, are always similar faces. An octahedron of fluorite, built up of a multitude of little cubes in parallel position, is a not very rare example of this. Parallel grouping is most interesting when the result is to build up a compound form with branching and rebranching parts like the limbs of a shrub or tree, and hence giving rise to a kind of structure called arborescent or dendritic. Here all the crystals or parts of crystals have their axes in the same direction. The common method of grouping of crystals, however, is quite irregular, and it is only exceptionally that twins or parallel groupings are noted. Minerals are not always in distinct crystals, like those of garnet or quartz, or even in aggregates of crystals. On the contrary, Many of the specimens in a mineral cabinet show no crystalline faces at all, and then they are simply called massive. There are, however, important distinctions of structure between massive minerals. First of all, the distinction between crystalline and amorphous must be well understood. A piece of clear quartz, or rock crystal as it is often called, is said to be crystalline. A piece of glass, which very likely the eye alone could not distinguish from it, is amorphous or formless. For the mass of quartz, though it has no definite external form, but is bounded only by irregular fracture surfaces, is just as truly crystalline in structure as a perfect crystal. This is true because the essential idea about a crystallized mineral is that there should be the regular arrangement of the molecules out of which it is built up. It is not always easy, often impossible, with the eye alone to decide whether this regularity of structure exists. It is shown by the cleavage, but when there is no cleavage, it is usually by optical examination in what is called polarized light that this can be most easily proved. For example, the bright colors given by a thin fragment of a quartz crystal in polarized light shows at once, to one who understands the subject of optics, that it is crystalline in structure. In the glass, on the other hand, the molecules have no definite arrangement at all, and hence no action on polarized light. The changes of matter which appear in crystallization, distorted and denuded of their grace as they are often found to be, still reveal great laws which never fail, and to which all change is subordinate, and which appear as such to accomplish a gradual advance to lovelier order, and more calmly, yet more deeply animated rest. Nor has this conviction, says John Ruskin in his somewhat fantastic and humanizing, yet graceful Ethics of the Dust, ever fastened itself upon me more distinctly than during my endeavor to trace the laws which govern the lowly framework of the dust. For, through all the phases of its transition and dissolution, there seems to be a continual effort to raise itself to a higher state, and a measured gain, through the fierce revulsion and slow renewal of the earth's frame, in beauty and order and permanence. The soft white sediments of the sea draw themselves, in process of time, into smooth knots of sphered symmetry. Burdened and strained under increase of pressure, they pass into a nascent marble. Scorched by fervent heat, they brighten and blanch into the snowy rocks of Paris and Carrara. The dark drift of the inland river, or stagnant slime of inland pool and lake, divides or resolves itself as it dries into layers of its several elements, slowly purifying each by the patient withdrawal of it from the anarchy of the mass in which it was mingled. Contracted by increasing drought till it must shatter into fragments, it infuses continually a finer ichor into the opening veins, and finds in its weakness the first rudiments of a perfect strength. Rent at last, rock from rock, nay, atom from atom, and tormented in lambent fire, it knits, through the fusion, the fibers of a perennial endurance, and, during countless subsequent centuries, declining, or rather let me say, rising, to repose, finishes the infallible lustre of its crystalline beauty, under harmonies of law which are wholly beneficent, because wholly inexorable. All crystallization, says the same writer again, goes on under and partly records circumstances of this kind, circumstances of infinite variety, but always involving difficulty, interruption, and change of condition at different times. Observe, first, you have the whole mass of the rock in motion, either contracting itself and so gradually widening the cracks, or being compressed and thereby closing them and crushing their edges. And if one part of its substance be softer at the given temperature than another, probably squeezing that softer substance out into the veins. Then the veins themselves, when the rock leaves them open by its contraction, act with various powers of suction upon its substance, by capillary attraction when they are fine, by that of pure vacuity when they are larger, or by changes in the constitution and condensation of the mixed gases with which they have been originally filled. Those gases themselves may be supplied in all variation of volume and power from below, or slowly by the decomposition of the rocks themselves, and, at changing temperatures, must exert relatively changing forces of decomposition and combination on the walls of the veins they fill, while water, at every degree of heat and pressure, from beds of everlasting ice, alternate with cliffs of native rock, to volumes of red-hot, or white-hot, steam, congeals and drips and throbs and thrills from crag to crag, and breathes from pulse to pulse of foaming or fiery arteries, whose beating is felt through chains of the great islands of the Indian seas, and makes whole kingdoms of the world quiver in daily earthquake, as if they were light as aspen leaves. And remember, the poor little crystals have to live their lives and mind their own affairs in the midst of all this, as best they may. They are wonderfully like human creatures, forget all that is going on if they don't see it, however dreadful, and never think what is to happen tomorrow. They are spiteful or loving, and indolent or painstaking, with no thought whatever of the lava or the flood which may break over them any day, and evaporate them into air bubbles, or wash them into a solution of salts. And you may look at them, once understanding the surrounding conditions of their fate, with an endless interest. You will see crowds of unfortunate little crystals, who have been forced to constitute themselves in a hurry, their dissolving element being fiercely scorched away. You will see them doing their best, bright and numberless, but tiny. Then you will find indulged crystals who have had centuries to form themselves in, and have changed their mind and ways continually, and have been tired and taken heart again, and have been sick and got well again, and thought they would try a different diet, and then thought better of it, and made but a poor use of their advantages after all. And sometimes you may see hypocritical crystals, pseudomorphs taking the shape of others, though they are nothing like in their minds, and vampire crystals eating out the hearts of others, and hermit crab crystals living in the shells of others, and parasite crystals living on the means of others, and courtier crystals glittering in attendance upon others, and all these besides the two great companies of war and peace, who ally themselves, resolutely to attack, or resolutely to defend. And for the close you see the broad shadow and deadly force of inevitable fate. Above all this, you see the multitudes of crystals whose time has come, not a set time, as with us, but yet a time, sooner or later, when they all must give up their crystal ghosts, when the strength by which they grew, and the breath given them to breathe, pass away from them, and they fail, and are consumed, and vanish away, and another generation is brought to life, framed out of their ashes. End of section 29.